Good morning again, folks. This is Mr. Everly, actually talking to you in the late evening, putting this video together for you for AP Physics. We're moving on to Chapter 6, which is Forces Part 2. Forces Part 2 includes friction and air resistance and all kinds of wonderful things. Now, you remember from last year, when we pull an object across a rough surface, there's actually two kinds of friction. So this is a graph made when say a book or something flat is pulled along the desk. What happens at first is that you start pulling on the object and it doesn't move because friction holds it in place. So we've got the book, you're pulling this way, and there's a force of friction back this way called the static friction. And as you pull, you increase your pull, increase your pull, increase your pull. The static friction actually gets larger to counteract your pull because the object, if it's stationary, has unbalanced forces acting on it. We have, of course, the weight force and the normal force as well. But there's a limit. There comes a time when you pull hard enough and it breaks free. So this is the maximum static friction right here. So I would call that F sub S maximum. And as soon as it breaks free, the inconsistencies, the roughness begins to ride along on top of each other. So the roughness of the table and the roughness of the book begin to bounce along each other, and the amount of friction dramatically decreases to a region called the kinetic friction. So as long as we're in this static region, the object's not moving. We pull on the object, we can pull on it as much as we want, but once we reach this point, we've increased the force to the point where we've reached the maximum static friction. The object can then break free of the surface and begin to slide, and it drops down to this kinetic mode. Okay? Now, the equations as we defined them last year were this, that kinetic friction, this kind of friction here, is equal to mu, a coefficient of friction, times the normal force. And kinetic friction is as simple as that, because kinetic friction is a really simple thing. It's constant for a particular normal force, therefore mu is a constant. The static friction is a different deal. Static friction can exist between 0 and some maximum value. So the maximum value of static friction again, depends on the surfaces in contact. So for a pair of surfaces, there is such a thing as a coefficient of static friction. And when I multiply that by the normal force, that is the maximum static friction. That's this up here. So static friction can actually exist between two values. It's going to be somewhere between 0 and some maximum value. And like I said, I kind of informally call this F sub S max. And I beg your pardon, this should be an S right here. Sorry about that. Because this is kinetic friction, this is coefficient of kinetic friction, coefficient of static friction. Now remember, the coefficient of kinetic and the coefficient of static friction is a constant. It has no units, because if you solve for it, check it out. Mu sub k is equal to F sub k over F sub n, and both of these quantities are measured in newtons. So newtons over newtons gives us a dimensionless quantity, which gives us kind of a feel for how much friction, what the surface characteristics are between two different materials. So remember, this is not a constant for a particular material. This is not something you can assign to, say, steel or asphalt or rubber or whatever. It's a pair of surfaces. So you could look up the coefficient of kinetic friction between rubber of a tire and the tar or asphalt in a road, and you can come up with that mu for that pair of surfaces. Same thing with the coefficient of static friction. Coefficient of static friction is a constant which describes a pair of surfaces, not a single surface. Okay, that's pretty much a review from last year. We've got these two types of friction. We didn't do a whole lot with static friction last year, but it's not that terrible. So let's do a couple of examples to speed you along your way. Here's one. This looks kind of lengthy, but we'll work our way through it. Okay. So the example says a box of bananas weighs 30 newtons and rests on a horizontal surface. Here's our horizontal surface, our box of bananas. It's got weight, and it has a normal force on it due to the surface. The weight is 30 newtons. So that's the mg over here. The coefficient of static friction between the box and the surface is 0.4. The coefficient of kinetic friction between the box and the surface is 0.2. Okay. First question says, if no horizontal force is applied to the box and the box is at rest, how large is the frictional force on the box? So nobody's applying a force this way. So this way, in order to keep this thing at rest, to keep it static, there'd be zero force. So A, the answer is 0 newtons. There is no static friction on it because there's no horizontal force attempting to cause the box to move. So that's kind of nice. What is the magnitude of frictional force if a monkey applies a horizontal force of 7 newtons to the box and the box is initially at rest? So we've got force of monkey this way of 7 newtons. And the question is, all right, is the monkey applying enough force to overcome static friction and break this box free from the surface? So in part B, what I think I would do first is get the maximum static friction. And that's mu sub s times the normal force. Now, if the weight is 30 newtons, I'm going to claim that the normal force is also 30 newtons. So that means the maximum static friction is mu sub s, 0.4, times the normal force of 30 newtons. Okay, so that is about 12 newtons of force. So in other words, we got monkey pulling this way, we've got static friction this way, and they have to balance out. Okay, the maximum static friction is 12 newtons. The monkey's only pulling 7. So that means the static friction is not yet up to the maximum. It's still 7 newtons. So it's kind of like this graph here where, you know, the monkey is only pulling this much. Therefore, the static friction is equal. It's killing off the monkey's force. So the answer to part B is 7 newtons. Okay. Next, what is the minimum horizontal force the monkey must apply to start the box in motion? And we've already answered that question. The maximum static friction is 12 newtons. He's going to have to apply at least 12 newtons to get this thing moving. D, what minimum horizontal force must the monkey apply to keep the box moving at a constant velocity once it gets started? So now we're into kinetic friction. Once this thing gets started, we're in this easy realm of kinetic friction. We don't have to worry about it changing from 0 to some maximum value. Kinetic friction is basically a constant for this particular situation. So we're going to say 0.200 is the coefficient. The normal force is 30 newtons, so the answer is 6 newtons of force. So if the monkey applies 6 newtons of force this way, coefficient of kinetic friction is now 6 newtons in the opposite direction, and this thing will move at a constant velocity. E, if the monkey applies a horizontal force of 15 newtons, what is the magnitude of the friction force? Now the answer is a little tricky because if the monkey is applying 15, the kinetic friction can't get any higher. Remember, that's a constant. So the answer is 6 newtons. F is, what is the acceleration of the block? Now we've got 15 newtons this way, and we still have only 6 newtons this way. So good old F equals ma kicks in. We've got the monkey force minus the kinetic friction force equals ma. So the acceleration is going to be monkey minus friction divided by mass. So we put our numbers in. Monkey force, remember, is 15 newtons. Friction is 6 newtons. And the mass is going to be the weight divided by 9.80 meters per second squared. All right, so it turns out that we got an answer of about 2.94 meters per second squared. Okay? It's a long example, but not a terribly difficult example, because the thing to keep in mind is if the box is at rest, the forces are balanced out. The monkey has to apply a force at least as big as the maximum static friction force in order to break it free. Once it's broken free, kinetic friction is the opposing force. And that stays the same, no matter how much force the monkey applies after that, how much more force the monkey applies, this remains 6 newtons. So the monkey can still apply 15 newtons of force, kinetic friction is still only 6, and then we can apply F equals ma to find the acceleration. So, not too terrible. All right, here's a problem from my wife. She said, cactus juice. So I've got a 65 kilogram crate of cactus juice to be accelerated at 7 meters per second squared up an incline, making an angle of 25 degrees with the horizontal. Okay. Okay, and we have an acceleration up the incline of 7 meters per second squared. The coefficient of kinetic friction between the crate and the incline is 0.2. How much force is required? So this is something from last year. What we're going to do is draw in the forces. We've got the weight of the cactus juice crate. We have the normal force, which by definition is perpendicular to the surfaces involved. We've got our applied force, which is actually what we're trying to find, and we've got kinetic friction. The next step is to take mg and break it up into 2 components. This is mg cosine theta. This guy is mg sine theta. Okay, so we have 2 axes. This guy's gone. We have 2 axes. We know that the normal force is equal to mg times the cosine of theta. We know that FA is bigger than the sum of these 2 guys because this thing's accelerating up the hill. So in order to write it, we're going to have to say sum of forces equals MA, or FA minus mg sine theta minus FK equals MA. Okay, so I've got this force up the hill, this force pointing down the hill, this force pointing down the hill. The sum of these forces then with their signs equals MA. We would like to know, what is that? What is the force we need to apply? Thing to remember here is that F of K can be replaced by mu times the normal force. And the normal force is mg cos theta. So I'm going to rearrange this puppy and say that FA equals MA plus mg sine theta plus the friction force, but I'm going to replace the friction force with mu mg cosine theta because F sub k is mu times the normal force, and our normal force is equal to mg cosine theta. So there is our beautiful equation in all its gory glory. Now, if we put our numbers in and punch this puppy through, I'll let you do the rest. It is 840 newtons. So see if that's what you get. I don't want this video to last forever, so we'll just move on here. This is actually one of your assignment problems in the text. It talks about scrambled eggs on a Teflon-coated pan. The coefficient of static friction between the Teflon and the scrambled eggs is about 0.040, really low. What is the smallest angle from horizontal that will cause the eggs to slide across the bottom of the Teflon-coated skillet? Now, this is a tough problem, but a really easy problem at the same time. So I wanted to just give you a hint as how to proceed. Imagine we take this pan and we go ahead and tilt it to some angle. And here's the scrambled eggs. Okay. If we just tilt it, there are no other forces acting on these scrambled eggs except the weight, the normal force, and static friction. Okay? Now, it turns out when we break this guy down, that when this is in a static situation, this force must equal this force, and this force must equal this force. Okay? Then the angle is made, a millionth of a degree bigger, and everything starts to slide. So what we are here is at the position where this is F sub s maximum. Okay? Now, our equation is F sub s max equals mu times the normal force. Or mu equals F sub s max divided by the normal force. But check it out. According to our diagram, the normal force is equal to mg cosine theta. Oops, let's put that on the bottom. And F sub s max must be equal to mg sine theta. So some really amazing things happen if you keep on getting rid of things. You find out that finding the angle is not that terrible. Last one. A 250-gram hockey puck traveling on ice at an initial velocity of 7 meters per second slides a distance of 14 meters before coming to a stop. Find the coefficient of kinetic friction between the puck and the ice. All right. So the only thing that makes this problem hard is the diagram, because we know the puck has weight. We know the puck has a normal force on it. And let's say that it's sliding to the right. It's got friction on it. Okay? Other forces on the puck, there are none. Somebody's hit this thing, and it's sliding across the ice. It's slowing down. If the ice were frictionless, this thing would go on forever and ever and ever, and the only two forces would be normal and mg. But there's friction on it. But we don't need a force here. A lot of students will want to put one there. We don't need a force to keep something moving. According to the first law, things move all by themselves unless there's an unbalanced force on them. Now, what we're going to do then is we're going to say, okay, well, the acceleration of this thing we can first find by doing a little spaceman spiff. So we'll say, okay, the initial velocity is 7 meters per second squared. It does this over a distance of 14 meters. The final velocity, 0. Spaceman Spiff says V final squared equals V initial squared plus 2A delta x. So we can solve for A by saying A equals V final squared minus V initial squared all over 2 delta x. And we know all this stuff. 0 squared minus 7 squared divided by 2 times 14 meters. Okay? And we come up with an acceleration of negative 1.75 meters per second squared. So, in this situation, finding the coefficient of friction means running home to Ma, because this friction force is slowing it down. Okay? And that friction force is equal to mu times the normal force. And the normal force is equal to mg. Okay? So what we end up with is a mu sub k equal to negative a over g. Wow, that turned out nice. So I've got negative 1.75 divided by 9.80 meters per second squared. So the coefficient of friction between the puck and the ice should be 0.179, I believe, if I have the numbers right. And no units on that, of course. So double check my calculations on that. I believe that is correct. All right. So those are my examples. I hope this makes sense. Please read the first part of Chapter 6. The first couple parts deal with friction. So I think if you read through Section 3, so not a whole lot of reading to get you there. And the problems I'd like you to do, let's see what I've got here. The problems are Chapter 6. Be sure to do the problems, not the questions. 2, 7, 8, 15, 70, and 87. And you'll find we already did one of those together. So it's actually a 5-problem set, kind of a normal size set. All right, this is the last of my videos for this week. I hope you're having a good week. I hope your sub is treating you well and you're treating the sub well. Take care of yourselves, and I will see you on Thursday, and we'll catch up. Talk to you later.